like I speak fast and I mumble, but she speaks slow and kind of doesn't mumble. But I think that's the thing that the Southerners do. We mumble a bit more. And we speak fast. Okay? That's really, what are you? Nice pen.
Are we waiting for you?
No. It's okay, we can just start. Okay, so L4, properties of definite integrals. So this topic kind of ties in together. It's kind of a good topic because it revises the quirky integration we did before. Do you remember when there was a composite function and the baby function was a linear? There was a particular method we used for that.
Yes.
And one where there was a composite function multiplied by the derivative of the baby. It was another kind of like style of integration. And also, do you remember like the, what's the integral of e to the x?
E to the x.
Yeah. And what's the integral of
1
over x? Yeah, ln x, yeah. That kind of thing. So it's it kind of goes back to that, but it's subbing in those numbers, subbing in the upper and lower limits and actually calculating the number as well. So it's kind of like a nice one. So this topic kind of ties in together a number of things we've discovered in this unit so far. For example...
Did we do that this year or last year?
This year. For example... That's nice. Okay, so on page 8. So if you happen to have all your notes, if you flick back, you might remember this anyway. On page 8, we discovered that something like the integral of 4e to the x dx can also be written as 4 and then the integral sign e to the x dx.
E to the x dx?
Yeah. And so if you take the numerical factor, like 4, it's just a factor of the whole function. It's just a numerical number that the whole function's being multiplied by. So something like that, we can take the factor or the coefficient or whatever it's called, the factor out the front, numerical factor outside of the integral. So we can write this. So this topic is general properties of integrals. We're going to go over some of the ones we've discovered so far on this page, and on the next page there's a few new ones, just a few new ones. And then we kind of practice using those. So in general, if that's the case, if the integral of 4x dx, 4e to the x dx can be written as 4 integral e to the x dx, how can we write this in general? This thing here.
Oh, I don't know. Yeah. You're going to tell us, aren't you, Miss
Is it a and then a tweety thing and then f to the x dx?
Yeah, exactly.
Oh, yes,
A and then our tweet. Perfect. Fx dx. And that's a nice property, so let's put it in a nice highlighted kind of, put it here, box. So there's about 1, 2, 3, 4, 5. So there's about 5 properties. So all 5 of them on this page and the next. And when we've kind of got the general property, I'm just going to kind of highlight it because it's kind of reasonably important.
So when you say properties, you mean like rules and probably different index rules?
Yeah, a bit like exponent laws, like how there's exponent laws, there's log laws, that kind of thing. Things that are allowed according to maths, the maths gods. The maths gods allow it.
The math.
Yes. So Kate, remember by mistake we were calling it a constant, but a constant's more like something you add or subtract at the end, isn't it? So think of it more so it's a factor, like a numerical factor of the whole function. Yeah.
Isn't it funny how it's not
Physics.
Yeah, I was just going to say physics.
Physics, yes.
We have a nephew.
Got a convection current.
And you should come and see us.
Today? Yeah. Oh, is it like a final as well?
No, well, there's a tournament, so it was different rounds, and then the one will be last. You should come.
There's so much netball at the moment.
Yes.
That's a very good point.
You should ask Dr. Fig. It's English breakfast.
Sorry.
Okay, so
the tea must be lighter than the water. Or the water that's constant.
yeah, there's no because it wouldn't be convection, would it?
Maybe it's
This being recorded.
Yeah. Okay, so
It's still something to do with school.
we're talking about
Tea.
we're talking about Krista's tea and how the tea bag is floating.
Why are you narrating
I don't wonder what's going on. This is Talise, Calvino, and Kieta we're talking to.
They don't care.
Okay, anyway.
And Katie.
And Katie, yes,
I mean, maybe
exactly.
it's just because they talk to tea bag. Did
you say
talk
to the
tea bag? Talk to the tea bag.
Okay, so at the bottom of page 17, so we're on page 23 now, but this was from page 8. At the bottom of page 17, we discovered that the below joke means
Zero.
There is no
you have no friends.
Yeah.
So this one here. So this happens to be another property. I'll scroll down a bit. So the general property is, notice that f of x, integral of f of x dx between the lower limit being a and the upper limit being a always equals?
Zero.
Zero, yeah.
Because there's no area between A and A because it's just the same number.
Yeah, exactly.
Kathleen. Hello.
Yeah, so we might want to make a little note of that. What did I write here? As you said, like make a little note of it if you want, in whatever way makes sense to you. So as the area curve from A to A on the x-axis is nothing.
You should have said there is no area.
Yeah, that makes sense, yeah. That would be grammatically better. Okay, so as the area under the curve from A to A is nothing. Don't write something like that in your IAs. I was going to say it doesn't exist, but it doesn't exist is kind of different, isn't it, to zero sometimes. So maybe that's why I changed it to nothing. So that's another little general property. That's amazing. That's a nice easy one if you get that one. It's like good, you just go, yeah, it's zero, move on. And then this is another flashback. On page 20, we discovered that we can split up a definite integral in the following way. So remember, if you're trying to work out the overall area definite integral, it's fine, but if it's the area, we have to split it up into this area, and then work out that one, and then add to it this area. Like the absolute value we need to add to it. So our lower limit is A, so that's A. Our upper limit is still B. So we might need to be aware of this little middle thing. What do they tend to call that one?
What? You just go.
Like the lower limit we always call A, the upper limit we always call B. But if you're splitting up two areas of the curve, like one below the x-axis, one above, they'll in the general formulas they call it C, the middle one C. So the lower limit's always still A, the upper limit's always still B, and in this general formula, we'll kind of like call the middle one C. So it's kind of like you're adding together the integrals of both of them, but like in a way like the absolute value of the integrals.
Like A, C, F, X, dx.
Good memory. Yep. So A, C, yep, F, X, dx plus.
Why did you say K?
I didn't say K.
Oh, A, here's today.
B, C, F, X, dx.
So, yeah, it is pointing out that you can add them separately. That's allowed. It works. So if it's necessary, you can do that. It's a thing that's allowed.
Are you sick as well?
No, I'm confused.
Everybody's sick. Sarah, bye.
Sure, you're sick.
Yeah.
I'm not stupid. You're not gonna catch germs.
And that's not gonna help.
Yeah, that's
What you should do is wash your hands every time you leave the classroom. Like I saw someone sneeze yesterday and it was bad.
Ew. But they go around and they wash the handles.
Like they do.
Handles.
But early in every morning.
I know, but like.
I'm conscious of that.
No,
I
during
sneeze,
like
I'm
cold
sick
season,
of
they
it.
do it in secondary
Have
school
you guys-
often. They
Yeah, but
figure
we're
out
in the
what-
secondary school.
Have you guys noticed that I haven't been sneezing in the past 2 weeks?
Yeah.
Because I used to sneeze every day, all day. I got to the doctor finally.
So here's the next page, top of the next page. So here are a few more properties of definite integrals. These ones you haven't seen yet. As in, these ones kind of like you sort of had an idea of because of stuff that you've seen before on page 8, 17, and 20. This is new stuff. So the definite integral of the overall function. So if you had two functions added together, like an f of x and a g of x, what do you think could be the case? What's the way you could split it up?
Estoy un poco
Oh, this might be
confundida.
So for example, the definite integral of the overall function is the same as the surf of the definite
Sum.
integrals, sum, or if it's the same thing, if it's a difference. So that's why they've got plus or minus here, because if they're subtracted, then you just split up the integral and subtract the integrals. If they're added, you can split up each integral and add them. So in general, so f of x is the first function, dx, and then you could write plus or minus in the middle, plus or minus integral of the other thing, which is g of x. And it's still the same boundaries. Still in the same. So just pointing out that if it's two functions added, it's two separate functions added together, you can separately integrate each one and add or subtract them, whatever it was. If it was plus, add them. If it was minus, subtract them.
Oh, so you just split up the formula.
Yeah. And that's if it's two functions sort of added together, like f of x and g of x, or two functions subtracted from each other. Yeah. It's just a thing that we can do. For example, this is not a new one, this is just pointing out an example. So we're not going to highlight this one here because it's just an example of that one. So for example, if you had something like integral between 0 and 2, x is 0 and x is 2, for 7x cubed plus 5x, you could split it into
The next one would be
the integral of this one.
integral 0 to 5x to dx.
Yeah,
Would be
exactly,
Okay.
Yeah, you're right. 0 to 5x dx. So no need to highlight that because that's not a new one. That's not a new property. Just an example of the above one. I tend to put, you have brackets when there's sort of two things added together. Because you know, like bedmass, without the brackets on 7x cubed plus 5x there, the 5x is the only thing with the dx.
But like, how come you would put 5x in brackets and then dx?
Because it's just one term.
Okay.
So that term for sure is being dx. That
Okay.
term for sure is being dx. It's when things are sort of added and like there's a number of terms added or subtracted. That's when you kind of like need to. Okay, similar. So yeah, and if that was minus, if that was a subtract in the middle of the bracket, you would just have a subtract here instead. So that's just something you can do. Oh, and then I said, let's prove this one using our calculator. So just to remind us how to use the calculator again, always good. Do a quick proof. So how do we find an integral again on the calculator? Let's grab our calculators. Yeah, Math 9. Yeah, so we need to keep just practicing calculator stuff just so we don't forget it. Because we're doing a bit of non-calc stuff today, so I thought I'll just insert one calc question. If you want, maybe you like, who wants to work out the answer to the first bit?
How come we just can't? We can't. Yeah.
Yeah, in a way, we're just proving that this one equals that one plus that one. But we can split up the labour. Does someone want to do the first one? Oh, you got it already? Okay. And then someone else maybe will do these two. I'll do the 5x dx. 5x, you guys are fast.
No, 38 is the whole thing.
So 38 is the whole thing?
Yeah.
So we're just proving that 38 equals the sum of these two. Hopefully. Let's prove it. Yeah, so we got 38 for this one. Equals. What did you guys get for that one?
No one did it.
That was
separately.
18.
Wait, that was 18. 28.
I can rest myself, but then you rest.
So that was just something I inserted so we don't forget how to use our calculator, like, because we're starting to do a fair bit of non-calc stuff. A little bit of calculator practice. Yeah, so see how we proved that they're the same. 38 does equal 28 plus 10, the sum of these two. Here's another new one. Here's another new property. Pretty crackers. If you switch the lower and upper limits of the integration, so if you switch the lower and the upper limits of integration around the other way, so yeah, we write this as a general property. So if you switch around A and B, what do you think?
Wait, what's the point of doing that?
Yeah, so if you do, yeah, what's the point of doing that? Imagine just the question was putting that to you in that way.
Negative 3a. Right?
It'd be what would it be?
Not for this question.
Oh, I thought we had to switch it.
No, we have a different question.
Sorry, I'm reading too much.
Oh, maybe you're thinking of this one, I don't know. So anyone want to guess what we would write as a general property? Just even a little guess?
Right.
Hmm.
Oh no, we're right. We
Yeah.
got the integration BA.
Actually, you're right. Put the negative first. Yeah. And then it's what?
BA.
Yeah, good. B then A. We'll flip those around. Swap those over. And then it's just fx dx. So just the main thing was that there was a negative out the front and that the A and the B got flipped. So that's a general. Oh gosh.
That looks special. Like, you get rid of it.
Yellow.
Special.
Yellow.
We can do it.
Yeah.
Yeah, I don't think it's one thing.
I don't think you're
I don't like cash because it doesn't really good with it.
I
That's
just
not
want
gonna
to throw it
affect
there. Just chuck it
I
there.
don't-
Okay, so that one, this is a nice easy one. So for example,
Why?
if, so for example, if we've got integral between 1 and 2, 3x to the 4 dx, how could we rewrite that using this?
Negative.
Yep.
Integrate. Integral. 2 and 1.
2 and 1, yeah.
And then you write the function.
Yeah, you write the same function, 3x, 4x. Yeah. So that's not a new property, so we won't highlight that in yellow. What am I doing here?
You put the one that you just wrote with calculator?
You could.
And then just add a sign to it.
Yeah, we're practicing one by hand. Because it's a nice one, the numbers aren't too horrible, like the
Bro,
function's
you
nice
mean
and
like,
small.
oh, this is what I like.
So this is good practice of doing it by hand now. So what we need to do is, we need to set up that thing
This is integrated.
with 2 and 1. Yeah, what goes in the square brackets?
3x, 5 over 5.
Yeah, the integral. Yeah, good. So in the brackets has to be the integral. 3x 5 over 5. 3x to the 5 over 5. And then we'll calculate that. I'll go across and calculate that. So equals. Let's go down a bit because it's a bit wacky down the end of the board. So what do I sub in first? The 1 or the 2? 2, yeah. Good. So sub in the 2 first. Correct the top one. And then what do I always do? I always
Can't you just have this into 16 up to 32? You subtract it from each other, right?
yeah, always subtract it. The upper limit subbed in, subtract the lower limit subbed in. Yeah, and so when practice, this is good practice for your fraction.
93 over 5.
Yeah, what's 2 to the 5?
32.
32, 32 times 3.
96.
Yeah, 96 over 5. Minus, what's that?
3 over 5.
3 over 5, yeah.
93 over 5.
93 over 5, yeah. What was one of these? Yeah, 93 over 5. I just forgot what the next thing was.
That was so ridiculous.
And then so we're doing that, and now we're proving that when we do this one up here, we get the same answer.
Oh, with the neck.
Yeah, like so if you want, what I'm going to do is, I'm going to, so say, imagine the negative's not there. Imagine the negative's not there. I'm just going to find the answer to this, and then just prove that it's the opposite sign.
Yeah.
Yeah, that would do
Drew
fine.
on the board. I made a little yellow.
Yeah, it is.
Do you want me to leave it there?
Yes.
Cheating and you
I thought you were going to say no, get rid of it now.
No, it's about
Saloni, bring it back.
No.
Let's go on.
And here's the evil anti thing. So let's do the, and then the 1 and the 2 are swapped around. And then it's still the same integral, 3x 5 over 5.
Integral backwards is logarithmic.
So you could do that. Oh, if you didn't want to just prove that they're the opposite sign, you could do this as well. So you could do that kind of thing to prove they're equal. So whatever makes sense to you. So what I kind of did originally is I just worked out this one and proved that it's the opposite side. But alternatively, you could just say the negative of all that, but to me that was more thinking. I didn't want to think. Okay, so. So then we've probably got 3 fifths. 3 fifths. 26 fifths. What's that equal to? 3 6 minus 96 fifths.
Yay! Wow, guys, we did it.
Super duper. So we proved it. If you have any space at all, you could write they are opposite sides. This is a little conclusion. So they are opposite. Same number, so we have proven it. Now we're on to just doing a whole stack of complicated examples. Yeah, you're gonna love it. Okay, yeah, cool. So we're going to use these properties to kind of like just do little shortcuts. So notice that in the question, they're telling us the answers to certain definite integrals. They're telling us that f of x dx, the integral of f of x dx between x is 1 and 3, x is 3 is 6. They're telling us that the similar integral, but for a different function, g of x, between that is negative 4. And that g of x, the same function as this one, but instead of between 1 and 3, it's 1 and 5, is equal to positive 5. So we're going to use that and the things that we worked out, the 5 things we put in yellow, we're going to use our knowledge of those to just work out what these answers are. So this one I've tried to make based on the first property that we listed on page 23. What did that one kind of stipulate?
We took a constant, a factor of.
Yeah, 5's just a factor, so we can chuck it out the front. So let's do that. Let's practice using those things. So 5's just a numerical factor, so pop it out the front of the integral. And do we know what, if we imagine the 5's not there, what would the answer be according to the questions at the top?
6. So do you just multiply it by 5?
Oh, close. Yeah, what would it be, negative 4?
Oh, you figure it out.
23.
Yeah, between 1 and 3, yeah. Whereas the 6 is from 1 to 5, yeah. So it's like saying,
Wait, what?
yeah, so notice that this one, the boundaries were 1 to 5.
I didn't
Whereas
say
for this one,
5.
the boundaries were 1 to 3. Oh, you said 6. Oh, you said this one, I get you. So it was more just, you just picked the wrong function.
Yeah.
So, yeah, I get you. Right. So what do you want to have a little guess what you think we might do? It's something really simple.
Just multiply.
Yeah, 5 times
Or I
negative
can't
4.
do
Yeah,
it.
exactly. And then we just write an answer. So these properties can make things that might look initially complicated quite easy, knowing these properties. B is based on the second one, I think. Yeah, this one has no friends.
Oh, I really want no friends.
The property that
I really want no friends. It's trying to
that was worse.
So Tekashi 6ix9ine released an album before he goes to jail. The idiot.
He what? What?
He released an album before he goes to jail.
That move? That's really good.
Tekashi 6ix9ine.
At least this one
Oh,
was
wait,
like,
what was he?
Because he was,
Maybe he needs it for protection money.
then he was, in his songs, he was talking about a gang, saying that he participated in killing like people in his gang, and people actually took it to heart, and like they said, yeah, it is a gang that's killing people.
but was he proven to be in?
He probably is like preaching the trial for that, so like, you know.
Okay. Anyway.
Yeah.
Sorry.
Smarter than you were released it before. Because at least then he could think pretty well. And also then he gets all the hate money from that.
That
Oh,
was a mess, Miss Brown.
yeah. So it's getting a bit complicated. So I'm just going to scroll back up because it's handy for you to see these things when deciding what to do here. So here's a different property. 3 to 5, does that appear in any of the blue integrals I've got? Could we make 3 to 5 somehow by adding sort of 2 together? And it's g of x. So could we do something with these two? So 3 to 5 is kind of like the gap between this one. If you add 3 to 5 to this one, you'll get that one, would you agree?
If I add what to what?
If I add this purple one down here to this one,
You would get 8 and
yeah,
4.
because the journey from 1 to 3 and 3 to 5 equates to the journey from 1 to 5.
Okay.
I'll go say that again because it's a bit new and weird. The journey from x is 1 to x is 3 and x is 3 to x is 5, if you add them together, it's the same as if you just went straight from 1 to 5.
Because the distance is 2, that makes 4.
Yeah, because 1 to 3, like say on the x-axis you're going from 1 to 3, you're getting the area there, and then on this purple one you're going from 3 to 5, you're getting the area there. If you add those two integrals together, it's the same as if you did from 1 to 5, which is pretty wacky. So, in a way, let's set that up as a little equation. We could say that this one, we could set up a little, I've given you a fair bit of space for this one. Oh my gosh. So let's say that this one is just this one plus
Yes,
this one
yes.
equals that one.
Yes.
And then the nice thing is we just sub in the numbers and we solve. So it's actually the maths we do is nice, but we're going to write a few little wacky things to start with. Ooh. Okay, so I'll use blue because that was one of the blue integrals. So start with 1 to 3 g of x dx plus, this is kind of like the what am I using? Okay, so anyway, okay, that one, and then this one, purple one, so the blue one up there, plus this one, this purple one, equals, I'm kind of cutting into that one, sorry, trying to draw it nice and small, is the same as the other blue, one of the other blue ones, oh gosh, I don't want a green one, or blue. So another blue one, which is, so going from 1 to 3 and then 3 to 5, the integrals are the same function. If you add those integrals together, it's the same as if you went all the way from 1 to 5. Yes. And so we're going to sub in some numbers and solve for the purple one. So you could rearrange this all now, but if it's awkward writing all that, maybe replace the blue ones with the numbers at this point, because that's kind of a bit easier, isn't it? So what number goes with the first blue integral according to
Negative
negative 4, yeah. And negative 4 plus the purple thing. 3, 5.
Don't do it.
Equals. What's the value of the other blue integral from the top of the question? 5, yeah. So
Complicated. So is it 9?
I just put it as x. I just put it as x.
if you want, yeah, and then yeah, you can.
5 plus 4 is 9.
Yeah, cool.
Seriously. Nice.
That's it.
No,
Okay.
got it.
So if you had another nicer way of sort of setting it up,
Four, and right.
so long as you can understand it.
9.
5, like Sarah said, 5 plus 4. So it
My
makes
teeth have been having real.
I'm sorry. I'm gonna make cookies. Did you go to the dentist?
I have healthy teeth.
So that's that. I might just separate off this one so it doesn't kind of get mixed in with the other thing.
Maybe I've had it once.
9:19. Okay, good. We've got time.
Just calculating.
Any questions about that one? Does that make any sense at all?
It's so complicated. Like I did one step.
Yeah,
What did you do?
you just can do that plus that, and then you sub them in. You don't even need to sub them in. You can just look at the top and write 4 or 5, and then you
It's
can
like
add.
5 to 1. If you minus 3 to 1, it's equal to 5 to 3.
Yeah, you could go
So I
straight.
just did
You can
5
go
minus
straight to the
4,
end.
and
Yeah, so yeah, exactly. You could go straight to, you could go straight to the video.
It's crazy.
Yeah. So you could totally go straight to the
Rain
video.
my book and go back to
Um,
run him.
Alrighty, so what have I done here?
No, it's just
So, does this look like any of the properties? Like
yes.
which property do you think it is from page
I think it's
23 and
page
23?
4. Property 4.
Property 4? It is! Property 4 on the top of page 25. What does property 4 kind of mean?
You have to add. So you're gonna have a function and you have to separate it.
Yeah. Like the integral of these two functions added together is or subtracted, yeah, sorry, yeah, exactly. Is equal to each of them separately integrated and then subtracted.
And we
That's that kind of thing.
can't do. And are we gonna have to take out? No.
Oh, okay, yeah.
We may have to take out a factor, do we? No.
Yeah, in fact, we can do that. Yeah, it's got the property 1 in there too. Yeah, so that would be in one of the next steps. So let's kind of split up the thing first, just to show that we understand what that property is. For g of x dx, and then it subtracts. So let's just write subtract. Yeah, that's just proving that it can be split up. And then, just like Chris has said, there's a numerical factor in the first one, so we can pop that up front. So let's do that now. Equals 4. Oh, hello. 2, 1. Q of x. Okay, so what do you think we then do as our numbery bits? What should appear in my numbery line?
That would be -4.
Yeah. And do I just write -4 or something else?
4.
Yeah.
Integral of -4.
Yeah, or 4 times -4, yeah, like that. Because the integral
Is that?
yeah, exactly, yeah. And then what do I sub in for this one? Yeah, -60. And what's our little answer?
-22.
You agree? Agree? Okay, that's -22.
It feels like what else
Yeah, isn't this fun?
Yeah.
Don't you like this stuff? It's nice, isn't it? The certainty of maths. Yeah, there's a certainty of it. Like something as awkward looking as that just becomes -22. And imagine being year 7 looking at that. They'll think you're geniuses.
-22 is kind of an awkward number though, TBH. It doesn't sit right with me. It doesn't look good. It upsets my chi.
Where is that girl? She hasn't released music in a good while.
It certainly doesn't upset Bella's G.
What's Snake
I
name?
swear she just remembered an album that no one paid attention to.
What's Snake name?
Yeah, look at that.
Did she have a pet snake?
And like
Yeah.
the snake was the album because everyone was like, Taylor Swift is a snake, and then she like embraced like that snake.
Why was she a snake? Because of the Kanye West and Kim K?
Yeah, and removing all the other things too.
Let's find out, guys.
She was
Like something with the age of her ex.
Yeah. And she like made those pretty hilarious with her accent.
Oh.
She was like
Who's she dating
one of
now?
her big.
Yeah, she released an album last year.
Yeah,
Cool Reputation. That's
Oh,
the
yeah.
I don't like
I think Nick Cave probably got an accident
Oh,
number
Like,
one.
like what you
In July 2018, Swift was cast in the movie adaptation of the musical Cats.
Oh, she's going downhill. You guys should come to support us in that book.
Alright.
So we have to do the negative of the one at the top.
Yeah,
we'll do that.
good. Bella, what did Sarah just say? What was her wise word?
See, Molly, you should pay attention.
Oh my God. Right on your
Fancy.
friend, Sarah.
Okay, yeah.
It's in the negative of the FX function
Why?
because it's switched.
Yeah, the A and the B got switched.
Yes.
So that
Oh, so you
is,
have to switch it.
yeah. So it was the negative of 3, 1, yeah, fx dx. well observed. So equals a negative what? What do I start with these?
Negative 6.
So in a way, it's okay if you just count like 6. Nice. That's a good one. So sometimes they might look awkward, but they turn out to be not so much work.
This is number 5.
I'll never do this.
The previous one was rule what?
The next one I don't like because it doesn't make sense to my little mouse brain.
Ah, yeah. So this one, it's got like a bit of the first one. So the first, what was the first property?
And the factor.
Yeah, the factor. What would be the factor? Is it 7 or is it?
Divide by 7.
Yeah, which can be expressed as
1/7.
1/7. Yeah. So our factor is 1/7. So that's one thing we could do. Was that what I did first? Yeah, I did. Okay. So 1/7 is our numerical factor. Then write all the other stuff. 5, 3. Then it's just g x minus 2. X. So that's all for the g of x minus 2. This kind of like is bringing in a little bit of transformations, like with functions.
Oh god.
Remember that x minus 2? What kind of, is that a horizontal or a vertical shift? When it's in the bracket?
Horizontal.
Horizontal. And horizontals in the bracket, yeah, they tend to be counterintuitive, don't they?
For
They go the
axes.
So
opposite
it is
way.
to the right?
To the left. Yeah. Oh yeah.
So, that's a good point. So, this is, we could say, you'll note, this is g of x translated horizontally, translated horizontally 2 units to the right. So in a way, it's going to bring back this function stuff. So this happens to be the same as g of x translated horizontally 2 units to the right. So, and the area under that would be the same. So the area under would be the same.
Under what? The translation?
Yeah, the area under that graph, the translated graph, would be, because it's shifted 2 units to the right, so it would be the same as if it was just g of x, dx, with the 1/7 down the front, of course. But, so because that has been shifted 2 units to the right, we could shift these 2 units back. So the limit's 2 units back.
Oh yes.
Yeah, does that make sense? Yeah, because that thing's being shifted 2 units to the right.
It's like it's grown.
Yeah. So g of x, according to this, g of x got shifted 2 units right, and its boundaries are 2 units right as well. So if we shifted it 2 units back to where it would be g of x, the boundaries would shift back as well.
So it'll
But we're
be,
not shifting.
so it'll be 1, 3.
Yeah, and all we're trying to do is use those integrals at the top to be
Yeah.
able to calculate what that would be. So the area under this thing, that you can see the 5, 3 dx minus 2 dx, would be the same as if we had it from 3 to 1. 3 to 1. Because this original function, 3, 1 dx dx, in here got shifted 2 units right.
Oh, I get
So
you.
it's down.
Oh, like, yeah,
Yeah.
okay.
Like, so its boundaries were initially between 1 and 3, but then suddenly it got shifted, like here, there's this little area, but then suddenly it got shifted to 3, 5, but it's still the same area.
Mm-hmm.
So see, if you took this original green function and its area underneath, you shifted it 2 units right, it'd be there. So it's the same area as if it was back in the green. So, but we'd have to use 1 and 3 and g of x instead. And the reason why we're bothering to do that is we were actually given that in the question, which means that we can actually sub that number in. So that was probably the most challenging question, I think, on this page. So then we just sub in the stuff we know. So equals 1/7. And what do we sub in?
-4.
-4, yeah. And what is -1/7 times -4?
-4 over 7.
Yeah. I'm a bit of a goodie. So See how they're a bit creative, like these ones? You sort of have to just experiment and have a little look around and that kind of thing. Tricky. Now we've got one more page to go. Oh my gosh, this was... Okay. This one is just practicing the quirky integration, but we're subbing in numbers. Like it's not like you just leave plus c at the end. We're actually going to sub in the lower limit and the upper limit. Sub her in. And here we go. So at this point, we should probably revise some more quirky integration from lesson 2 and try applying it to definite integrals. No calculator as well to make life hard. Feel free to use calculator to check. So what did this diagram tell us again? Integrate this, you get that?
Integrate, you get that.
Yeah. And, oh sorry, it's the other way, sorry, differentiate that way, integrate that way, just because of this one. Yeah, integrate this one, you get that, differentiate that one, you get that. Do you remember things about x? What's the, x has to be greater than? 0, yep. Because you can't take the log of a negative number and you can't take the log of a of 0, because e to the power of anything will never equal 0. And e to the power of anything will never equal a negative. That kind of thing we have to think of as well. So to make it a little bit, when I typed this up, it looked a bit weird, so I put the function in blue, just to make it clearer which part's the function. Otherwise, when I made it all one color, it looked like 23 was going on here. So so I've put the functions in blue just to make, because the formatting in the book's better, but on here it wasn't coming out so well. So this one is, to start with, we might want to use, we could be able, there's a way we can turn this into that by using property 1. But what's property 1? Yeah, take a numerical factor out. What could be, what have we multiplied this by to get that thing 3? So we'll start by taking 3 out. So let's do that. So equals 3 to 1 of x again. 3, and then we just pop 3 out the front. So feel free to make a point of what you did as well, because maybe you might look back at this and go, what? So if you want to write a little note while you did it, you do that. Or just leave it off. Okay. And now we can integrate this thing. So now we set up our box, you know, the box where we put the integral in it. So, and don't forget the 3 out the front. So maybe you want to put the 3 in to begin with, or else we might forget it. And in the box goes the integral. What's our integral going to be? ln x, yeah, exactly. So when we're finding a definite integral like this, we don't bother with any plus c's. So we're subbing in the numbers, and don't forget the little numbers, cube, again, 2 and 1. That's just the notation we use. So worth writing that step, because if things get messy on the next line and you get a mark for doing this, you want to be able to get that nice mark. Oh gosh, maybe write a bit smaller than I am. Oh, that's not too bad. So we've got to separately sub in ln2 minus ln1. So I would suggest have the 3 at the front to begin with if you want. It's much easier. And then work out the ln2 minus ln1 minus ln1. And then you're using log laws. Yeah, what is ln2 minus ln1? What do you do?
Log equal. Oh, yeah. Divided.
Yeah. Yeah, you divide these two numbers, don't you? When you subtract, if you were adding the logs, you would multiply them. So when you're subtracting the logs, yeah, ln2 over 1, I'll just show that as working out, equals 3 ln2, obviously. And we don't have an x there at all, so we don't need to define x as greater than anything. It's just a number. 3 ln2 looks weird, but it's actually just a number. And if it's non-calc, you just have to leave your answer like that. Because e to the power of something, we don't know what it is that equals 2, it'll be a weird decimal. If it was something like ln1, you know that this is 0. Because e to the 0 equals 1. But we can't work that one out, so we're done. That's nice. Did I write anything else? No. If you want to make a note, like you might want to say use log laws. Use log laws to combine. That might be something you might look back on and not realise what you did.
Isn't it L8?
Good idea. Oh, it is. Yeah, you could also write it as ln8. Yeah, that's acceptable as well. ln8 is also acceptable, and why? That's a good point.
To bring the 3 back.
Yeah. ln2, 3. Yeah, you can put that up as an exponent, which equals ln8. Yep, so both are good. Quite up front. Both are good. Like they're also fine with 3l and 2. Just be aware they might require you to turn it into that. So just be aware you can do that.
If they say in the simplest form.
Both to be honest are considered nice and simple. Okay, so both would be accepted. But imagine they just said, write your answer as ln x. What is x kind of thing. So they could do that.
Yeah, so
Yeah, so that the way that's more important. And then next, oh god. Okay, so that's the easy x. But, or like easy, what have I got instead of x?
T.
Yeah. And is it just e to the t, or have I made a composite?
6.
Is that a composite function?
60.
Yes.
Yeah. It's a composite function.
U, the baby is 6T and the mother is E to the U.
Yeah, exactly. Is the baby linear?
Yes.
Yeah, 6t is just a linear function, like 6t plus 0.
Yes.
So it's one of those ones with a composite function with a linear baby. So let's make a note of that. So this is where we have to use that nice phrasing method. Composite function. Composite with a linear, you could say linear sub n, or if you just want to write baby, because it's how you remember it, that's fine. Baby u.
I might just pass out or recess.
Absolutely.
So a composite function with a linear baby. So remember the way we kind of do this, the way I've kind of set it up is, let's define the mother. The mother is
The mother what?
e to the u, like you said. That's the mother. The baby, what's the baby?
6T.
Yeah, 16. I think to do the baby in green, it's just nothing. 16, and then I think I'll write what they all are. And we need the derivative of the baby.
Yeah.
Oh, actually, no, you know what? Even better. I wrote it like this. U equals 16. And then I tend to write u dash. What is the derivative of the baby? Yeah. So I tend to write out those three things. That one just to remind us is the mother. And is the baby. If you don't like using mother baby, just have to look at it. And then we need to integrate the mother. So I do write that in purple. And then we integrate integral of the mother.
Don't you mean the derivative of the mother?
Integrate.
Why didn't we do the derivative of the mother and
I
just
did
the
this a
baby?
while ago. It was like you integrate the mother and derive the baby, and then you like smush them back together and put the baby back into the mother. That sounds really weird.
And it's actually, so you integrate the mother and you multiply the integral of the mother by the reciprocal of the derivative of the baby.
So one of the same.
Yeah. That's it. There's a bit of messing around. It's like the chain rule, but for integration instead. Kind of think of this as like a chain rule for integration. The integral of the mother is a nice one at least. E to the u, yeah, that's a nice one.
But then you end up with a really gross thing.
Yeah. So yeah, you can have a gross thing. So I then do 1 over the derivative of the baby times by the integral of the mother is what I write as my next step. And then we've got to sub everything in as well at the end too. Yuck. Gives us, so I might just work with that here. What's 1/6 times e to the u?
Even you over 6.
Yeah, and what is u? I might just put that in now.
What is you? It's
6T.
Yeah, equals good. E to the 6t over 6. That's our lovely integral.
It's gross.
Yep. And now we've got to start to work out that integral.
It looks like it says ETT.
Yeah.
What is that? The
I'm running out of space. So that's a 6t there, sorry, that's 6t. So now we've got to work out the integral, with the numbers subbed in. So it's et, okay, e60, sorry, over t, and now we've got to sub in 1 and -1. I'm just running out of a bit of space here, so that's
Why is it over T?
Oh, I don't know. Sorry, that's weird. Okay. Oh no, now it's frozen. It's like the board didn't like what I wrote.
Always towards the end.
Yes.
Okay, so what are those brackets for? We're integrating?
Yeah, because we've integrated and now we're just subbing in 1. So subbing in 1 and then subbing in -1.
To find a definite.
Yeah, I'll just have to close and open again. Yes, I do. Please.
It's okay, Miss Lily.
See, if I don't save it, I'll have to save as on my desktop. Come on. Oh, great. Now the computer's seizing up. So basically, you're subbing in.
So this doesn't make it work.
Just want to write it on the board.
What's going on with the network? Something's up with the network. Yeah, I think I'm going to have to write it on the board, sorry. And we'll just talk everyone through it.
Remember when this little cut?
Yes, that one time that was so funny. Miss Maloney.
Wait, what?
What's that?
Look
Look at what's happened here.
Oh, we're taking this back to Miss Lily.
Miss Maloney, Miss Wilcott wanted to watch a video on one of those
Look
like
at this.
online websites that are like Netflix, like the illegal ones.
Illegal.
Yeah, and she accidentally downloaded a virus, and the virus got into the whole school network, and she gave the whole school this virus.
Yeah.
The